And now let's try to solve this equation and to understand how you can have how the qubit works and how we can create a 1 qubit gate for that. So this was the equation we just mentioned, right? So what should we do? We want to convert it into the matrix form. But we are not going to go through the detail again because we tried that last time. But what I'm trying to say is that now I'm going to use cosine phi. I'm going to use cosine phi hat equals to half e to the power I phi hat minus e to the power negative I phi hat. Remember this? We discussed this last time for the Cooper pair box without external voltage source. Remember this? Yeah? The reason we use this is what, if you remember, right? Let me see if you remember. Was because of this. Ei phi applied to n will give me n plus 1. E negative I phi applied to n will give me n minus 1. Correct? Do you remember what we learned last time? What is n? What is, again, what is n? N hat, what is n hat? What is n hat? Number operator. Then what is this state n in our context? The eigenstate of the number operator. Physically, what it means? Not there, yes, not there yet. When we construct the matrix, this will do that. But what I'm asking is, physically, what is the meaning of n in this circuit? Huh? Extra, the Cooper pair, like extra pair of Cooper pair, excess Cooper pair. So it can be negative, can be positive, right? You take one away, it's negative 1. So you go from negative infinity to infinity. Right? This is just a review. We discussed this before. So you use this one, and we repeat what we did before, and now go back to what you just say, the off-diagonal stuff. If try to find the matrix M, the elements for the Mn row equals to n, no, yeah, equal to n, but delta Mn, right? M need to equal to n in order to be non-zero. And last time we also say that M applied to e to the power I phi n equals to delta. You need to have M, how to write that? M equal to n plus 1. If n equal to n plus 1, then it is non-zero, right? And similarly, e to the power negative I phi n needs to have m equal to n minus 1. And that is the off-diagonal, one row up what you just said. Okay? Then we also limit to 2 levels. Okay, and just please repeat what we did last time. Repeat. Repeat what we did in Cooper pair box with no voltage, no VG, right? The no VG case. We repeat that, then we will get the Hamiltonian in matrix form for 2 level only is going to be, I'm going to write this out, right? So we only have n equal to 1 and n equal to 0. You're going to have 4 EC, 0 minus ng square, 0, 0. Plus 4 EC, 1 minus ng square, 1, 1, minus EJ over 2, 1, 0, plus 0, 1, right? If you go through the math, you will get this, but I think you should appreciate why we have this, because this one has the n hat, and it only is non-zero on the diagonal terms, right? So I need to have, when n equals 0, this is 0, 0, n equals 1, this is 1, 1. These are diagonal terms. And they have the corresponding n minus 0 minus ng, 1 minus ng. And these two terms, they are only non-zero if they have offset between these two, m and n, right? Either 1, 0 or 0, 1. And we don't care about negative 1 and 2 state because we limit ourselves to 2 levels in this case. And that's why I get this, right? I also now define, which we also did that before, but now make it explicit. ECC equal to 4EC, which means this is equal to the charging energy of a Cooper pair, of one Cooper pair. Of one Cooper pair, right? Which makes sense because it is equals to half. Now Cooper pair have a charge of 2e instead of e squared divided by c, right? But of course the c here, as you know, we have been talking about, it is the c summation plus cs, right? But we just keep it as c here. This equal to 4 times 1 over 2e squared divided by c. That's why it is 4ec, right? So I would like to write it in this way. So as a result, this one is going to be ECC times ng squared. The diagonal is ECC times 1 minus ng squared. Of diagonals are going to be negative EJ over 2, negative EJ over 2, right? This is 4EC, so it's ECC, ng squared. 4EC, ECC, 1 minus ng squared. And then these two off diagonal terms. Again, you should recognize this. This is exactly the same as what we had last time. Except last time with an ng equals 0, so this term is 0, and this term is just ECC. Question? C is the, which capacitor? Then we need to go back, right? It is the, which one? Oh, I see what you mean. Yeah, this one, because we kind of change it. So it is this one. C summation plus CG. Yeah. So it will be all of them. Other questions? Okay. So with this, we have Hamiltonian. We can solve the equation of motion, right? But we would want to do one more step. So let me write it down again. I should actually copy it. So we have H equals to ECC ng squared negative EJ divided by 2, negative EJ divided by 2, ECC 1 minus ng squared. My goal is to shift. I want to shift it. Shift the energy level. Or energy reference. So that the 0, 0, or let me just call it E0, E1, right? E0, E1. When I say E0, I'm talking about E0, right? E1, I'm talking about this. I do that so that it is symmetric. They are symmetric. about 0. That's the goal, right? So maybe originally this is -1, this is -3, for example. I want to shift my reference, so this becomes 1, this becomes -1. -1 to -3 has a distance of 2. I shift the reference so that they are so that reference is at -2. Then this will become 1. It will become -1, and that is the idea, right? So that's why we're trying to subtract the whole thing by a constant, a diagonal constant, and this has no problem because again, any diagonal constant only change the global phase of the system. It won't affect the physics. So because of this, you go back, right? I'm not going to derive it or look at the book. I define EFH equals to E0 plus E1 divided by 2, right? Just like what I said just now, we have -1 and -3. I add them together, -1 plus -3 divided by 2, which is -2, right? So this is the FH. So I'm trying to shift it. With this shifting, then eventually I come to this equation. Okay? Just need to take it for granted. You go back to do the math if you don't trust me. Now I'm going to do one more step. Okay, I'm going to define E equal to ECC times 1 minus 2NG. This equation, we need to keep referring to it later. We just define something called E equal to 1 ECC minus 2NG. And after we have done this, maybe you can tell me, right? This is just equal to, H hat dash is just equal to half of negative E, negative EJ, negative EJ, and E. Become very beautiful, right? I mean, we're pretty symmetric. Because again, I take out the half for each element. So this becomes 2ECC, 1 minus 2EG. So this is just negative E. Similarly for this one. Right? So this is the very neat equation. Let's pause a little bit. Any questions? So what we're doing is to find the Hamiltonian of a Cooper pair box, but we only limit to 2 levels. And we are going to work in a valid regime that this 2 level actually is very accurate or even exact later. I will show you, which is the charge qubit. Okay? And how do we do that? We did not do anything special. We did not learn anything new. All we have done is just start from this Hamiltonian and then represent it in the number basis. We go through all the equations we learned earlier and do an energy shifting. We come up with something very neat. H dash equal to negative E, and then negative EJ, half. Is this clear? Any questions? If no, then we can look into this equation. Right? This is very beautiful now. Why? Let's look at this equation in this way. H dash hat, right, equal to half negative E, negative EJ, negative EJ, and then E. I can decompose this into a linear combination of the Pauli matrix, right? And you can see that right away by just inspection. This equal to this minus this. Do you agree? Right? You just plug in, yeah. Off diagonal, negative EJ divided by 2. Diagonal, the first one is negative E divided by 2. The lower one is E divided by 2. Right? Then we can further write this as this. Negative EJ divided by 2 sigma x minus E divided by 2 sigma z. Right? Nothing special. But isn't that I also can write it as negative 1/2 sigma x, sigma y, sigma z, Ej0E if I want, where I basically define, or I can rewrite this x sigma dot E, not E, dot BE. This is just the inner product of two vectors. But first of all, are you okay with this one? Row times column, right? So basically, you are just getting sigma x times Ej, and then sigma y times 0, and then plus sigma z times E. That gives you this expression. Is this okay? Right? This is just a vector, inner product with another vector. When you do inner product, the first one is row, right? The second one is column, like bracket, right? And this is the poly vector we learned quite a long time ago, sigma vector. And this one is also a vector. I deliberately write it as a B, like a magnetic field, subscript E. Is this magnetic field? No, this is just energy. Right? Its unit is also energy. But however, this one is so similar to what we have learned in spin qubit. In spin qubit, we say that you have spin, right? And its Hamiltonian is just the Pauli vector times the external magnetic field, inner product, scaled by the gyromagnetic ratio and divided by the h bar, etc. Right? But we can write it in this way. I don't claim this is a B field yet, but I write it as B. But is this okay? So now I simplify the Hamiltonian or re-express the Hamiltonian of this circuit. Come on, this is just a circuit. There's no magnetic field at all, right? And this is a circuit. If you did not learn quantum mechanics, just try to use it as a compact model. It's just a pure electrical circuit. Right? You can simulate in LT spice, actually, right? You just plug in the JJ equation. But now I tell you that the energy of this circuit is equal to sigma dot B, right? Which is pretty interesting. We've gone through a long way eventually. This one resembles a spin qubit. If we look at the spin qubit, it was negative B dot gamma spin, right? And then eventually equal to sigma dot B. This is our charge qubit. It is equal to sigma dot BE, of course. Sigma dot BE, we need to make this very clear. BE vector is equals to E, J0E. It is not, it's completely energy. It is not a magnetic field. It's not a magnetic field at all, right? And we also can define its magnitude BE as square root of EJ square plus E square. Again, it's not magnetic field. But however, right, if we replace B, whatever B, by BE, should be what? Divided by gamma H bar. Am I right? I mean, for every B, we substitute with BE by gamma H bar. Then the spin equation will become the charge qubit equation. Right? Spin qubit equation will become the charge qubit equation. For example, this guy, I replace B by BE divided by gamma H bar. Gamma H bar will get cancelled. Then I get the Hamiltonian of this system. Right? So the message is that whatever we have learned before can be reused here. For example, in the spin qubit, we know that if you have an external magnetic field of B, what will happen to your spin qubit? What's that mechanism? What do you call it? Larmor precession, right? Is qubit the Larmor precession has a frequency omega L equals to gamma B divided by, that's it, gamma B. I forgot all the math. So then what do you think? Then it means here we also have the charge qubit precess about this fake magnetic field. It doesn't matter if it's a magnetic field. And a Larmor frequency of gamma B E. I say we need to replace gamma B, replace B by BE divided by gamma H bar, right? So it's going to divided by gamma H bar. So it's equal to BE divided by H bar. It will precess in this frequency. Is the unit correct? Yes, because H bar omega L is energy. Our BE here is energy. Right? So I will stop here, but now the beautiful thing is that I can map this to the broad sphere. And instead of external magnetic field, now I replace this by this fictitious magnetic field, which is not real magnetic field, right? Because it's energy. But we can just write down the direction of this B vector, and then we can describe how the qubit will precess on this broad sphere. Okay, but we will continue next time, and then we talk about the single qubit gate. Okay, any questions from online and here? Yeah. Yeah.